Before we begin studying semiconductor devices like diodes and transistors, we first need to understand a very important concept, which is modeling. Almost everything we analyze in electronics is based on a model and not on the real physical device itself. Understanding what a model is, why we use it, and when it fails is one of the most important skills for an engineer. So, what is a model? A model is a simplified mathematical representation of a real object or process. Instead of dealing with every single physical detail of a device, we describe it using equations that are easy to analyze. Think of it this way: a real object would have numerous factors affecting it, and modeling each of those factors mathematically would be too complicated and often unnecessary for our goal. Whereas the model is simplified, but an important distinguisher is that it also must capture important behavior. A model allows us to predict how a device behaves without examining every single atom inside it. So let's just take an example. Uh, Say a resistor. So if we purchase a resistor from an electronics store, the actual resistor is made up of physical materials and they have many complex properties. However, in a circuit, we usually replace it with an ideal resistor, which we all know is V is equal to I into R. So where V is the voltage across the resistor and I is the current through the resistor and R is the resistance which is measured in ohms. This equation is the current voltage relationship of an ideal resistor. Instead of worrying about the resistor's material, shape, or manufacturing process, we simply use this equation. So this is the resistor's model, which we use for all, not all, but most of our use cases. So models are not, so as we know, models are not the reality. One of the biggest mistakes students make is we say a real resistor is V equal IR. That is not true. This equation is only a model. An actual resistor behaves differently under different conditions. Say a temperature changes. When the resistor becomes hot, resistance changes, so R is no longer a constant. So under high temperature conditions or now under very high current, if a large current flows, the resistor heats up and the voltage current relationship becomes nonlinear. So in this case, V is not equal to IR. So therefore, the model has its limitations. So we must always know when a model works and when it does not. See, for most cases, V equal to IR is sufficient. This does not mean that this is not a valid model. We just need to know in which use cases we can use it. So if the use case does not involve high temperature or does not involve very high currents, V equal to IR is perfectly fine. So another question that comes to mind is why use models at all, right? Like why not just, represent the physical phenomena as they occur. So if models are imperfect, why do we even rely on them? Because models make engineering possible. Because good models help us to analyze, predict, design, and improve. So, in the case of circuits, we can analyze circuits, we can predict their behavior, we can design new systems, and we can improve existing designs. Without models, every new circuit would require endless experiments, and instead, we um like we should be able to predict how a circuit should perform before building it. We shouldn't have to perform empirical experiments on every little tweak we want to make. We should be able to predict how it would behave given a tweak. So now that we know why we need a model, what makes a good model? A good model should satisfy two goals. One is accuracy, and the other is usefulness. So, a model should represent reality as close as possible. The more accurate the model, the more reliable its predictions. But the second goal is a model should also be practical and um, easy to use. So, if a model is mathematically too complicated to solve, it becomes less useful to everyday engineering work. So, engineers would prefer models that are, that allow quick calculations, that use simple equations, and provide physical insight into how a device works. So, but now we might think, right, that accuracy and the usefulness aspect of it seem to be contrarian. There is unfortunately, there is a trade off between accuracy and simplicity. The more accurate models are usually more complicated, require more equations, more math, and take longer to solve by virtue of the fact that they have more complicated mathematical equations. And simpler models are easier to solve but often less accurate because they may be oversimplified. Hence, for this reason, we can develop multiple models to represent the same device. And for the same device, there may be a simple model, an intermediate model, and a highly accurate model. So, what would be a useful measure in this scenario would to make a hierarchy of models, and then we just choose the one that best fits the problem at hand. For example, we are calculating the current in a simple resistor network, then V equal to I into R is perfectly adequate. But if we are designing a precision sensor operating at high temperatures, we might need a more detailed resistor model that accounts for temperature effects. So basically, the choice depends on application. So, why understanding physics matters? The best models are built on a solid understanding of the underlying physics. When we know why something happens, we can create models that will predict what will happen under new conditions. These models allow us to improve the devices, to invent new technologies, and to solve problems that have never been encountered before. Prediction Prediction is one of the greatest strengths of scientific modeling. So, uh, there are still areas of science where underlying physics is still not fully understood. As a result, reliable predictive models do not yet exist. And another like analogy of picking the right model, um, according to the use case, would be the example of the Earth and how we model it. So, a useful way to understand modeling would be to look at how our understanding of the Earth has evolved. Centuries ago, different models of the Earth existed. One assumed that the Earth is flat, another assumed that the Earth is round. Both models explain certain observations, right? Like the uh, ancient people who believed that the earth was flat made the assumption of the basis that for as far as the eye could see, the earth looked flat. You couldn't like predict the earth was round from near like naked vision. However, the round earth model explained many observations and enabled better predictions. So, it is said that Christopher Columbus accepted the idea that the earth is round. So, based on this model, he believed that sailing west from Spain would eventually reach Asia, right? Because, and this belief gave him the confidence to undertake his journey. However, the model he used was still imperfect. Combined two major errors. It underestimated Earth's diameter. It did not include the existence of North and South America. And even though the model was incomplete, it was useful enough to support exploration and decision making. So, this illustrates an important point. A model does not have to be perfect to be useful, it only needs to be accurate enough for the problem being solved. Why we, however, even though, oh, I wrote it in the wrong thing. Um, okay, there we go. Okay, so we know that objectively saying the Earth is flat is wrong, but we still use the flat Earth model. So today we know that the Earth is approximately spherical, but for many everyday engineering tasks, we effectively assume that the Earth is flat. Why? Because over short distances, the curvature of the Earth is so small that we can safely ignore it. For example, while designing a small classroom or while designing a small house, treating the earth as flat introduces negligible error while making calculations much simpler. Mathematically, this is linear approximation, right, of the more accurate spherical Earth model, and that is valid over a small region. In electrical engineering, this idea is similar to using a small signal model or an incremental linear model, where a complicated system is then approximated by a simpler linear model within a limited operating range. So, the main reason is that there is no single best model, right? So there are many different models and each are designed for a different purpose. Some are simple, some are simple and fast and approximate, whereas the others are detailed, highly accurate and mathematically complex. So one of the most important engineering skills is learning to choose the model that provides sufficient accuracy without um, unnecessarily overcomplicating things or unnecessary complexity. So let's just summarize what we've learned today. A model is a simplified mathematical representation of a real device or a physical system. And a model has its limitations and is valid only within a certain range of conditions. A good model should be both accurate and useful, although these objectives often conflict. And to combat this, we frequently develop a hierarchy of models, selecting the simplest model that is sufficiently accurate for the task. So, models must be built on a sound understanding of the physical underlying principles to provide the best predictive capability and support the design of new technologies. And successful engineering depends not only on creating models but also knowing which model is appropriate for a particular problem. So that's it for today's lectures. See you in the next lecture.